Okay, hello, welcome to another one of my video log recording sessions where I talk about genetic algorithms. Sorry. Yeah, so where I talk about genetic algorithms. Well, all the way from the basic stuff and onto the intermediate stuff, and hopefully onto some advanced stuff in the future. So, in my previous videos, or one or two of my previous videos, last videos, I was talking about how different distributions used for sampling the utility values and the constraint values would affect the peak level and the plateau level across different max constraint percentages. Yeah, and I did kind of whine and complain that because there are 8 different distributions that one could sample from, there would be 64 different combos, or in this case products. Well, minus the 8, because I've done those 8 cases where both the utility values and constraint values were sampled from the same distribution, sampled separately from the same distribution. So I only had 56 to go through. However, while doing that, I thought, why not just do the entire 64? It wasn't going to take that much longer. It was already going to take that much so long. So another 8 additional combos, distribution products wouldn't have mattered that much. So that's what I did. I iterated through the 64 combinations, namely, can I get, well, here right now here is like a spoiler, but anyway, I'm going to show it. So here are the 8 distributions, just as a reminder. First is normal, and then log normal, and then it's uniform, and then it's exponential, and then it was von Mises, and then it was Pareto, and then it was Weibull, and then it was left skewed. So there were 8 to begin with, and 8 times 8, because if you choose one for utility values, one for utility values. Why is my brush like this? One for utility values, and one for constraint values. So that's 8 times 8, which is 64. Cool. So, and I'll briefly show you the notebooks that I used to do all this. It's these 4 notebooks. So each one of these notebook files would have 16 different distribution products. Yep, you can see as it says here, 7 out of 16 done. And so each one of these 4 files would have 16 distribution products, and they would be running simultaneously, or rather all at the same time. Although there were some technical difficulties regarding the compute units on Google Colab Pro Plus. So I often had, maybe not that often, but I did have some occasions where the runtime just ended and I had to find out what was done and what was not done, and continue on, rerun and continue from there. But after about 70 hours or 60 something, 60 plus hours, I got everything. I got around 197 files, when I should actually have 192 files. But those 5 surplus files were because of some overlaps due to the runtimes being disconnected and me having to run these notebooks again, and therefore the notebooks creating the same file again. So those were removed after, and after that, well, those were removed by using this notebook. I didn't do everything, by running Python code, but I did get to figure out what I actually had more of by running this notebook. So I'm going to first show and record what I did, and then go through the peak plateau plots, all of the 192 peak plateau plots, not like one by one, but get an overall overall review of the patterns or their behaviors. So first, when all the files were done, 197 of them, first I create the distribution list: normal, log normal, uniform, expovariate, von Mises, Pareto, Weibull, and left skewed, and then make the products and end up with 64. And then that's what I get. And here towards the end are the timestamps, but I don't actually need the timestamps, so I would try to figure out what I'm trying to do here is count the number of files per distribution combo used, per distribution product used. So in the end, I just had to make sure that normal had 3 files, because it's normal 10 items, that's 1, normal 40 items, that's 2, normal 100 items, that's 3, as you can see here. Normal 10 items, 40 items, 100 items. Same thing goes for every distribution product, such as here: expovariate normal 10 items, expovariate normal 40 items, and expovariate normal 100 items. So that's 64 times 3 is 192, and this whole process was just to make sure that I have 3 items, 3 JSON files per distribution product. And I did that, and I summed it up, just in case, and I plotted them through this process, maybe somewhat convoluted, you could say. And then I wanted to get a subplot, a plot containing 192 subplots, and voila, here are the pictures. Yep. So first, normal, 10, 40. The leftmost is 10 items, in the middle is 40, the rightmost is 100. And we go from normal log normal uniform, normal expovariate, normal von Mises, normal Pareto, normal Weibull, normal left skewed. So that's exactly like this: normal log normal uniform, normal exponential, and on and on and on. Oops. So here are these plots. This is a bit hard to see, so let's bring it up here and have a look. So this is something that we have seen before, so we'll just skip this. Normal log normal. Yeah, somewhat similar to this, as the dip size increases at 10 items, but at 40 items they do somewhat converge, and the behavior between 40 items and 100 items with this distribution product is almost the same. Normal uniform, again the same. Normal uniform, 40 items and 100 items. Let's go to paint. And hello. Let's reshape this. Oh, what happened? I wanted to use paint, so I'll be using paint. Wait for it to load. It is a big picture. I don't know why it's doing that. Come on, I need the whole thing. Yeah, and it should end with left skewed, and currently I'm not getting that. Because why? It's a big picture, so seriously? Okay. My bad. Go on above and then get the other picture, which is this all 64 of them? Can I open this in Paint? Yeah, I'll just use this. Please work. That's gonna take a long time. Just bring it all up to here and check that I have everything. I don't. Okay, that's frustrating. And here's what we're going to do. I'm going to lose this, erase that, and then I'll just be switching back and forth. So, as I've said, it ends with left skewed, 10 items, 40 items, and 100 items. And so, normal uniform, about the same. So right now, what we usually see is, let's just try to generalize. We have the axis. We have the axis, and then the plateau level will just, for 10 items, it will just go something like this. Something like this, right? And for the peak level, it'll just go something. Peak level, it'll just go something like this towards the end. This is This is the max constraint, and this is the util sums, or the average of sum, well, summed util, or the average of summed util, right? This is 10 items. Technically, that is wrong, because the peak should always be by definition higher, so it should go something like this. This is at 10 items. At 40 items, oops, at 40 items, the plateau level will just be like this, and the peak level will just be something like this, usually. Or the plateau level could also be something like this, and the peak level could also be something like this, and rather kind of like that. So that's what we're seeing, and this is the same for when we have 100 items or 100 genes, and we'll see this happening quite often, very often actually. See, it's either this or this. You know, it's either some variation of this or this at 40 items or 100 items, and we'll see that now. So normal and uniform, something we've seen. Normal and exponential variant. Yeah, again. You know, this looks kind of unusual, but you know, it's nothing out of, you know, it's nothing that's wildly different. What about normal and von Mises? Same. Yeah, and normal and Pareto, same. Normal Weibull, same. Normal left skewed, same. Normal log normal, same. Log normal, we've seen this. Log normal uniform, same. Log normal expovariate, again, same. Log normal von Mises, same. Log normal Pareto, 10 items, 40 items, yeah, about the same. Log normal Weibull, yeah, this is kind of unusual, but overall, except for this, it's the same. Log normal Weibull, same. Log normal left skewed, again, kind of unusual, but still the same. Only this bit. Uniform normal, same. Uniform log normal, same. Uniform, same. Uniform expovariate, same. Uniform von Mises, same. Uniform Pareto, same. Uniform Weibull, same. And I'm just going to just speak when something is different. All these are the same. Okay. 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 Nope. Yep. For Mises left skewed. Same pattern, same behaviors, all very similar patterns and behaviors. Wow, this is a bit different. Pareto von Mises. But the well, this is volume. Yeah. Pareto and von Mises is different, kind of. Pareto and Pareto. Available. I wonder why this happens. About the same. This one's a bit strange, but it's not an entirely different breed. Available von Mises. Same. Same. Left skewed. We're in the last 8. Okay. What was that? It just shut off. I don't know why. Well, thank God I have it on tape. Last 8, is normal, normal, variate, von Mises. Yeah. So not everything kind of behaves the same way, except maybe in this case, Pareto von Mises. Yeah. But apart from that, even that's not like totally entirely different. I mean, the slope can be said it's different, but it's not like a different species or anything. Yeah. So, another thing to note is, I think I might have dealt with this or spoken about this last time, but what seems to happen quite often is that if you look here, relative to the red dotted line, which is the maximum, which is the total sum of utility values for this run, as the number of items increases from 40 items to 100 items, or rather 10 to 40 and from 40 to 100, the percentage, well, the relative size of the blue line, or even the gold line, the yellow or gold line, the peak level and the plateau level, are closer to the total sum of utility values when we have 10 items than when we have 40 items, which is about like all this much, and this is 80 something, 85, and the plateau level is at about, below 60. Here, with 100 items, using von Mises log normal, von Mises and log normal, von Mises for the utility values and log normal for the constraint values, and when we have 100 items, the plateau level is above 200, maybe 240, let's say. No, is it? No, 210. 220-ish. And the maximum and the total utility sum, total sum of utility values, is above 350. Whereas this was 85. Below 60. 60 divided by 85. So this is about 1/3. This is more than 1/3. However, we have what, 36-ish. Okay, let's just say this is 35, and we have 29 out of 35. So that's 28. 35 is 4, 5. So that's 80%. 7 times 5 is 35. 7 times 4 is 28. So that's 80%. 60 out of 85 is less than 80%, and 220 out of 350 is about slightly more than 1/3. I'm just undoing these, and this seems to be the pattern across all these different distribution products. And well, this is a bit different. It's a bit more round, this one, exponential and log normal. But anyway, even here the relative level when compared to the total sum of utility values is lower as the number of items gets bigger. Maybe not here, they're about the same, but it is still lower than when we have 10 items, speaking of exponential and normal. Yeah, it's the same. Across all distribution products. So I think that's just safe to say that. So I've thought about the reason why this might be happening, and it was just the very obvious one. It's just that as the maximum constraint percentage increases, there were fewer and fewer procreation happening, and therefore less innovation, and everything was just up to mutation. Mutation did all of the, all the work when it comes to producing entities with higher summed utility values. So and when that happens, it doesn't usually work out that well. Oh, yeah. So right now I'm working on, or rather tweaking some code to ensure that some amount of procreation happens even when the max constraint percentage is high, and therefore no entities are being struck out because of the selector at work. And what I hope to see, or I'm hoping to see, and what I am seeing, is something like, and I'll repeat myself in my next video, but it's something like max constraint percentage and summed util average, maybe 10% of 10%. And what I hope to see is something like, if this is the sum of total sum of utility values, as the maximum constraint percentage goes up, I need the plateau level to go up, and I also need the peak level to go up. And because this is the average of top 10%, this is the average of summed utility values of the top 10% entities, it won't actually be none of these lines would actually be touching the ceiling, that is the total sum of utility values, but I need them to be very close, and I need the slope to be always positive. And that's what I have been seeing, but I need to know what I need to do in order to ensure that this happens. Yeah, so that's that. So, and this is the result of around 70 hours of coding and computation, and what something like $100 gets me on Google Colab. I don't know if my money was worth it, but hey, this is just for practice, or some experience with Google Colab Pro Plus. Yeah. So hopefully, with the new way of evolving things, with a new evolution scheme, I can make sure that that this happens. And when I make sure that this happens, once I have made sure that this happens, I'll make sure how to control dips. I'll be one step closer to controlling dips, controlling the size of dips, or eliminating dips. That's because that's why this started. Dips. Okay. Thanks for watching. See you in the next video. Why? ¿Por qué? Okay, see you in the next video. Bye.